Okay, hello everyone. Last time we had started an introduction to light, and I think I'll start again, going a little faster, but I think I'll start again from the beginning. Are there any questions before we dive in? On and off a light bulb or the light from the sun, right? We're familiar with different colors of light. There's a profound realization a few hundred years ago that it's actually that light is the vibration of electric and magnetic fields. It always has the same speed called c. A small wavelength. Okay, that's this equation. Okay, the speed of light is equal to wavelength, Greek letter lambda, stands for wavelength times frequency. So if you have a small wavelength, you have a large frequency, because when you multiply them, you have to get the same number, c. And for a large wavelength, you have to have a small frequency. Okay. And then finally, we'll talk about how light is composed. In fact, and this is the theory of quantum mechanics tells us this, light actually isn't continuous. It actually comes in little packets called photons. So, right, we talked about how one example of different wavelengths or frequencies of light are the different colors. And if you shine white light through a prism, you see it creates a rainbow, showing that white light is in fact invented by our brains. It's what our brains invent. It's kind of an invented color whenever our eyes see all the colors of the rainbow together. It looks white. But beyond that tiny sliver of visible light of red through blue, there's all kinds of light that we can't see just because our eyes never evolved to be able to see it, to sense it. But we have other ways of sensing it, like radio waves, microwaves, infrared. Those all have longer wavelengths and lower frequencies compared to the visible spectrum. And then higher frequencies or smaller wavelengths, ultraviolet, X-rays, and gamma rays. Okay, so the visible light we see is a small sliver of the full electromagnetic spectrum. And so let's go through each of these bullet points here. Light is a wave of electromagnetic fields. And what I mean is something like this. This is kind of a, it's difficult to illustrate this, but this is kind of the best way we can illustrate on the screen of a computer what an electromagnetic wave is. That is, you have an electric field, that's what causes charges to move, like electrons. Electric field gets large in one direction and then large in the other direction. It oscillates back and forth. And with it, a magnetic field is changing. That you're familiar with, right? It's what causes a compass needle to move, or if you played with magnets, right? So magnetic field, strong in one direction and then strong in the other direction, oscillating back and forth, okay? And it's moving in this picture to the right at speed c. And that speed c, as I said, is frequency times wavelength. And frequency, by the way, frequency stands for oscillations per second. So another way of writing the frequency is 1 divided by capital T, which stands for the period. That is how long it takes to oscillate over one period. In other words, if you have a really large frequency, that means that T is very small. It means that how long does it take to complete one oscillation? Just a very small amount of time if the frequency is high. And to understand what a wavelength is, so this is, if we were to look at this wave in space, you can see what the distance is between peak to peak of the strength of that electromagnetic wave as it oscillates to strong and weak, strong, weak, strong, weak. So this is lambda, is a wavelength, peak to peak, or equivalently trough to trough. But not only is the wave wiggling in space, if you just look at any given point as that wave passes through, that's one way of illustrating that it's waving in time, right? So if you look at the wave at a given point in space, the wave as it passes through it is going, is oscillating in time. Strong weak, strong weak, strong weak. And how long does it take to complete one oscillation from max amplitude to min back to max is called the period T. Okay, and the frequency, again, if you have a small period, if it doesn't take long to oscillate, that's a high frequency. So frequency is 1/T. And we can put all this together just to illustrate both wavelength and period together and how they're related. So here's a wave moving to the right, and we see that as it moves to the right, at a certain point, it'll repeat itself and it'll look exactly the same. Okay, that corresponds to one period. Okay, so one full period is the time it takes for it to move one wavelength. Okay, and we can piece that together to explain this relationship that I said as one of those bullet points, which is that C equals lambda f. The speed of light has to equal, the speed of that wave has to equal the wavelength times the frequency. And so that means the wavelength times the frequency is fixed. And one way of visualizing that is that the speed of light is like the area of a rectangle. I say the area of a rectangle because a rectangle has length times width. So you can think of like the width as lambda and the length as frequency. You multiply frequency times lambda, the area has to be the same, has to be speed of light. So you see another example on the right-hand side of a rectangle of the same area, but it has a large frequency and a small lambda. In other words, its length times width has to be the same. So because the speed of light is fixed, this just tells us that if we know the frequency of a wave, then we know its wavelength. Higher frequencies correspond to smaller wavelengths. Smaller frequencies correspond to higher wavelengths. Okay? And so in different contexts, right, sometimes when I talk about light, I'll talk about its frequency, okay, the frequency of light. But you should always understand that we could use this formula to equally talk about the wavelength of light, because if you know the frequency of light, you know the wavelength of light. Okay, or other times in this course, I'll talk about the wavelength of light. But that's the same thing as saying the frequency of light. Those are not independent. They're once you fix one, you know the other. Vice versa. Okay, so this is the electromagnetic spectrum, and what you see, as promised, is if you look at, say, radio waves, which are on the left here, on the left are waves of large wavelength. So radio waves have huge wavelengths. They can be kilometers in wavelength. And what does that mean? That means that it's going to have small frequencies. Okay, so low frequencies in hertz. Now, a hertz is the unit corresponding to cycles per second. Okay, hertz or Hz just means cycles per second. So if I rub a comb through my hair, it gets a little electrically charged, and I wave it at 1 hertz, 1 cycle per second, I'm producing a radio wave. Okay, radio waves with really big wavelengths are emanating from that comb at the speed of light.
So the bigger the wavelength, the smaller the frequency.
Mm-hmm. Yeah. So radio waves, like, now I don't know, everyone now, like nowadays, maybe people don't use radios as much, but maybe in your car, you still have a dial that has radio in kilohertz. That's FM is in kilohertz, meaning thousands of cycles per second, or megahertz. AM is in megahertz, millions of cycles per second. We consider that a low frequency when it comes to radio waves. All other, or when it comes to light, all other wavelengths, frequencies of light, I mean, are higher, much faster than that. So radio waves have the lowest frequencies, but the longest waves. And that's why you need a long antenna to catch radio waves. Like on your car, your antenna sticks up a few feet. It needs to be big in order to capture those big radio waves. And if I go to the other side of this electromagnetic spectrum, gamma rays, those are like the opposite of radio waves. They have the highest frequencies, way higher than trillions of hertz, trillions of cycles per second. Actually, hundreds of trillions of cycles per second correspond to visible light in the middle. Gamma rays are way higher than that. And they have tiny, tiny wavelengths, way, way smaller than the diameter of an atom. Okay. So any other questions about the electromagnetic spectrum?
Where would you find gamma rays at? Like, where would that exist? Is it on Earth?
Yeah. So yeah. Actually, let me talk maybe about. Let me give a brief overview of where you find all of these waves. So, like I said about radio waves. So first of all, so I'll go from left to right in this picture. We will see lots of examples of radio waves being produced by astrophysical phenomena. So we'll talk about that. But other than that, radio waves mostly come from humans who produce oscillations of charge in antennas to produce radio signals. And microwaves, we'll see a very famous example of that later on in the course when we hear about the cosmic microwave background. And essentially, we're all being bathed in microwaves right now from all directions that are the remnants of light still reaching us from the Big Bang. But other than that, the only main source of microwaves are humans who produced radar. So radar is usually between radio or microwave frequencies, and what's in your microwave oven at home, which used to be called a radar box. Okay, and microwaves have wavelengths about a centimeter or two. And actually, you can see that if you put like a stick of butter or a candy bar in your microwave, you might see like places where it's melting and then not melting and melting and not melting. That corresponds to the length scale of you can actually kind of see the wavelength of light in your microwave oven if you do that experiment.
Oh, really?
Infrared is and we'll talk about why this is later on in the course, but infrared is the type of light that things at room temperature emit. So we are all emitting lots of infrared, which we associate with warmth. So if you're sitting by a fire and you're feeling the heat, that's infrared. And also just the heat from a human body is infrared. And that's how we can use infrared cameras. You know, to see someone through a wall, you can see like the warm glow of a body from infrared. Okay. Now we're also associated with visible light. Light bulbs and the sun produce visible light. Visible light is produced, along with ultraviolet light, are produced when electrons in atoms change energy levels. We'll actually talk a little bit more about that today. But so essentially atoms emit light waves that are in the visible and ultraviolet spectrum. X-rays are produced when, so when you get to X-rays and gamma rays, those are both examples that can be produced when you get radioactive decay of an atom. So you have, now we haven't talked too much about radioactive decay, but this is when the nucleus of an atom breaks apart. So as opposed to ultraviolet and visible light, which is produced when a whole atom, like the electrons that are orbiting the atom, emit light, X-rays and gamma rays can be produced when actually the nucleus inside an atom breaks apart. And so you get those from radioactivity, and the other source you get them are from particle accelerators. So humans create these beams of charged particles that we accelerate to very close to the speed of light, and we use those to produce sources of X-rays and gamma rays. That's how you get an X-ray at the doctor's office. There's a little particle accelerator that slams electrons into a piece of lead, and then when the electrons stop, you get a shower of X-rays. So that's my little overview, but if you have any other specific questions, I'm happy to move those down.
I have a question. What size of waves can get into a human? Does that make sense?
So it depends what you mean. So a lot of these waves just pass through us, like radio waves. So when you're driving your car, radio waves are constantly moving through us. Your antenna can tune into those radio waves, but in terms of the human body, it's as though they don't exist. Microwaves are similar. They are absorbed very weakly by the human body. They can warm you up because in the same way that a microwave oven can warm you up. So for the most part, microwaves pass straight through the human body, but a small amount of those microwaves do get absorbed by the human body and warm the human body up. Now, you may hear about, conspiracy theories about phones and microwaves causing cancer or doing bad things to the body, but we know as physicists that at worst, what a microwave can do to the human body is warm it up a little. In fact, in hospitals, they used to have basically big microwaves to warm patients up who were cold. That's literally, that's how it heats up food. And that's to some extent how we can see precipitation and weather images from radar, because the radar microwaves get absorbed slightly better by rain. But all it does is just warm you up a little bit. Then when you get to infrared and visible light, that's absorbed better than microwaves. So actually, those are in some sense more dangerous to humans than microwaves. And you feel that also as warmth, but they only warm up your skin, right? So you get in sunlight, it's absorbed so well that it doesn't get too far into your body. It just warms up your skin. And then when you get to ultraviolet and X-rays, then they start to go back through you again. So ultraviolet gets absorbed by your skin pretty well, and so that can cause skin cancer. But when they start to go through you is when you get to X-rays, and that's how you get an X-ray. They go through your body really well, except bones absorb them a little better. And so that's how you can see your bones in an X-ray. And the gamma rays go through you almost completely. And in fact, we're all constantly being hit by gamma rays from what we call cosmic rays that are coming from outer space, which is something we'll talk about later in the course. And it's one source of cancer that we actually can't get away from. We're just constantly being bombarded by X-rays and gamma rays from space, essentially. Any other questions? Okay, so let me ask this question for you to get some participation credit. And I talked about the frequency, right? And I talked about a couple ways of, some terminology regarding frequency. Okay, so the frequency of a wave. So we talked about how, what are ways of defining frequency? Well, cycles per second. One way of talking about cycles per second is the number of peaks passing by any point every second. We might call that a cycle. So you could A would be an answer. B, cycles per second would be an answer. C, hertz. Hertz stands for cycles per second. That's the unit of hertz. So C would be an answer. And then D is maybe the trickiest one here, but you probably get the impression that the answer is all of the above, because one way of expressing the frequency is if you know the speed of light and you know the wavelength, then from that formula we talked about, you know the frequency. So in fact, it's equal to the speed of light divided by the wavelength. So the answer here is all of the above. Okay, I'll give you 5 more seconds. So most people got all of the above. Okay, and then the last thing I wanted to mention in terms of that overview of light is that actually, it turns out, and we can do this experiment here at NEIU if you become a physics major, we do this in our lab courses. If you take a light bulb and you start lowering the brightness of the light bulb, so you turn down, you have like a dimmer switch, and you turn it down and you turn it down. If you turn it down so low, at a certain point, the light stops getting less bright continuously, and you start seeing little blips. Blip, 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 blip. And those are called photons, okay? It turns out that there's a minimum strength of light called a photon, that it comes in little packets. And each of those packets has an energy given by this formula. It's some constant called Planck's constant h times the frequency. And so this is important in understanding things like how I was just talking about how microwaves can't really hurt you. That's because this formula tells us the energy of a photon of microwave light, because we know its frequency, and its frequency is pretty low. Okay, and that frequency, that energy of an individual photon. So if you turn down a microwave, you see it's composed of these packets of energy that each one has such little force it can't ionize an atom. What that means is that all the atoms in your body, at worst, what happens when they get bombarded by microwaves is they start to jiggle a little bit. And that's warmth. They get heated, okay? Whereas something like ultraviolet radiation, that has a high enough frequency that the energy of ultraviolet light is such that when a photon hits an atom, it can knock an electron out. That's called ionizing radiation, and that can cause cancer because when you knock electrons out of atoms, that allows them to form bonds. They can snap onto other atoms and reconfigure the molecular structure of something in your body. Okay? And that's what causes DNA to get mutated in cancer in cells. Okay? But anything before ultraviolet, visible light, microwave, infrared, radio waves, we call that non-ionizing radiation. All it can do is warm you up. Okay? Can't do anything else. Of course, warming someone up can be dangerous if you warm them up too hot, but other than that, it's considered safe by physicists. Okay, so here's just another visualization of this quantum hypothesis. This was discovered about 100 years ago now, about exactly 100 years ago when quantum mechanics was first developed. In other words, when you have a lot of light, it looks like it's varying continuously when you dim it down. But if you have a little bit of light, it becomes clear that actually it's dimming down in steps. And that's because at a certain point, it's all composed of finite numbers of photons. So what I was just belaboring, the point I was belaboring a second ago is that the shorter the photon wavelength, that's another way of saying higher the frequency, the higher the energy of the photon is. Okay, and that comes from this formula. The energy of a photon is proportional to the frequency, which in turn, like I said, because if you know the frequency, you know the wavelength. So high frequencies correspond to small wavelengths. So either way, you can say the same thing. Small wavelength has high energy, or high frequency has high energy. So any question about light before I talk a little bit about the matter that light can interact with, right? Because light is pointless without something to interact with.
So is photon and wavelength kind of interchangeable?
So photon is a name for, not wavelength. A photon is a name for the smallest packet of light. So light ultimately, like, you know, when you turn on a light in your house, you don't see it because there's trillions and trillions of photons. Okay, so it looks like your walls of your house are uniformly illuminated. But if you were to turn the light down so low that you would need sensitive particle detectors to detect it, you would see that the light was coming out randomly, like whoop, 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 in these little packets called photons. Okay, those photons are photons of light, and they have a frequency. And if right, but frequency is cycles per second, and if you have a high frequency, you have a short wavelength, and vice versa. Okay, and so those are properties of light in general, but it's not another name for the word photon. Any other questions? Okay, so matter. It's important to understand a couple of, like what are atoms made of, right? So one of the important things is this concept of electric charge. Okay, this is where the electric field comes from that we talk about when we talk about electromagnetic fields of light. Electric charge, an example is like an electron, okay, or a proton in the nucleus of an atom. Turns out that charges are what we call quantized, so meaning like those packets of light, charge comes in packets. Okay, an electron has one negative unit of charge, a proton has one positive unit of charge, and that unit of charge is this number, which is called, well, the unit is called a coulomb. Okay, and the fundamental unit of charge is 1.6 times 10 to the minus 19 coulombs. And opposite charges attract. So an electron is negatively charged, a proton in the nucleus of an atom is positively charged, and they orbit each other, right? Electrons are orbiting the nuclei of atoms because they're oppositely charged. And if you try to bunch like charges together, whether electrons or protons in one place, they want to repel. So they attract and repel based on their charge. And there's a force between them, right? So what is the force? It's very similar to Newton's law of gravitation, except it depends not on their masses, but their charges. So the force law is called Coulomb's law. It's some constant times the charge 1 times charge 2 divided by their distance squared. So just like Newton's law of gravitation, we say this force is inversely proportional to the square of the distance between charges. So if you get charges far away from each other, the force is less strong. This is intuitive, right? Things interact when they're close together, not when they're far away. So this is why you get atoms and molecules, okay? You get atoms because you have positively charged nuclei. That's what's shown here in the middle. And these negatively charged electrons that orbit those nuclei. And that's great. That's basically the origin of all complexity in this world. And what holds tables together and cells together is all due to the attraction and repulsion of charges in atoms. For example, molecules, right? Like H2O, water. That's due to the attraction and repulsion of electrons in atoms, allowing them to kind of snap together into various configurations like Lego blocks. Now, so everything in this world is made of kind of combinations of these atoms that snap together in various ways. Atoms normally are neutral, so that's why like my hands aren't snapping together because one has positive or negative charges. No, the atoms in our hands or in anything tend to be neutral because those electrons are orbiting those protons, so that overall they're neutral. They have no total charge. Right? Now you can create a little transfer of charge like with a comb through your hair or something, and that tends to transfer little electrons to the comb so that you have a little bit more electrons on the comb and too few on your hair, and then they attract each other, and that's why your hair gets attracted to the comb. But generally atoms and things are neutral, which is nice. It means things don't just stick to everything. This is a basic picture of an atom. You have this nucleus, and what I want to get across here is that this cartoon here is very, very oversimplified of an atom. A better picture of an atom looks like this. Better because the nucleus is tiny. Okay, the nucleus is 100,000 times smaller than the orbit of the electrons. So here's an example of a whole atom. The size of an atom is about 1/10 of a billionth of a meter in size. So that's what's shown here. But the nucleus is 100,000 times smaller than that. Okay. And then this too is a bit of a simplified picture of an atom. So I'm also just going to show you the kind of closer to being true picture of an atom, which is that these electrons don't really orbit like planets. Really, this gets into the subject of quantum mechanics, which I'm not going to teach you quantum mechanics in this course, but the very basics are that when you try to measure the position of one of these electrons, you don't find it orbiting in a nice little orbit. You find that really, when you measure it, it shows up randomly, like in a random point in what we call a probability cloud. Okay, so if I tried to visualize what an atom really looks like when you actually try to measure it, it looks something like this. Okay, nucleus in the center, and when you measure where the electron is, it's kind of randomly found in this kind of cloud around the nucleus. And okay, one of the properties of the atom that I just tried to get across that I really want you to take away with you is that compared to the size of that tiny nucleus, the orbit of the electron is about 100,000 times greater. So the atom as a whole is about 100,000 times larger than that tiny nucleus in the center. Now, what is a nucleus made of, right? So there's these negatively charged electrons orbiting this tiny nucleus. The nucleus is made of two things. It's made of positively charged protons. That's a positive charge, so that the electrons are attracted to those positive charges. Now the electron orbits the proton primarily rather than the proton orbiting around the electron, because the proton is much more massive, so it doesn't move very much in its orbit. And there's another particle in the nucleus besides the proton that's about the same mass. So it equally adds to the mass of an atom, and that's called a neutron. And it's called a neutron because it's neutral. It doesn't have charge. Okay? So all the neutron does is add to the mass of an atom. It does not add to the number of electrons that need to orbit it to make it neutral. So a nucleus is made of neutrons and protons. And overall, what I'm talking about now here is the periodic table of elements. When you look at the periodic table of elements, what determines what makes hydrogen different from helium, or helium different from carbon? Well, it's the nucleus. The nucleus can have some number of protons, and each number of protons corresponds to a different element. 1 proton is hydrogen, 2 protons is helium, 3 protons is lithium, and so on. Okay. 6 protons is carbon. Okay, and then that's called the atomic number, Z. That's the number of protons in a nucleus, and that determines the chemical properties of an atom. Because if you have, say, 3 protons, that means you have 3 electrons orbiting, and that's all. Those electrons are what interact with and snap together to form molecules. So the properties of the atom are ultimately determined by the atomic number, the number of protons. And then there's another property of an atom, which is how heavy is it, and that's given by the total mass. And the total mass is given by the number of protons plus the number of neutrons. That's called the mass number. Okay, the mass number A is the number of protons, atomic number, plus N, the number of neutrons. So, if you're going to label an element in the periodic table, you can give it a symbol like nitrogen, or you can give it a symbol like carbon. Each symbol, like carbon or nitrogen, corresponds to some atomic number. So, nitrogen, for example, has 7 protons. That's where the 7 goes, down here. Carbon has 6 protons. So you see the 6 there. But additionally, for each number of protons, you can have different masses. You can have different, what we call isotopes, different total masses. So you can have nitrogen 13, meaning you have 7 protons, but 6 neutrons added to the 7 make a total mass of 13. Carbon, you can have 6 protons and 7 neutrons, so that has the same mass as nitrogen, but it's carbon. Or you could have carbon 12, so 6 protons and 6 neutrons makes a total mass of 12 there. Okay, and so those are all the characteristics that go into different elements. And so, like I said, they're like, you have the element of carbon, but you have different isotopes of carbon, some of which are heavier, some of which are lighter. That's determined by the number of neutrons. Okay, so I talked about isotopes. Okay, an isotope is when you have some nucleus of a given atomic number, say carbon, so 6 protons, but you can have different numbers of neutrons, and it's the same, has the same chemical properties because it has the same number of electrons and protons, but you're just adding these neutral neutrons that changes mass. So, for example, hydrogen, right? This is the simplest element. And element number 1 in the periodic table is hydrogen. It has 3 isotopes. Okay, there's the most familiar, that we just call hydrogen, and that doesn't have any neutrons. It's just 1 proton. So you have 1 proton with an electron orbiting it. That's hydrogen. But we have 2 isotopes. One's called deuterium. Okay, deuterium has an extra has 1 neutron. So now it's twice as heavy as hydrogen. Okay. There's something called heavy water. Okay, if you make water, which is H2O, but instead of hydrogen you use deuterium, well, you're using something that's twice as heavy as hydrogen. Okay, that produces a type of water that's just heavier than normal water, called heavy water. That's used in the nuclear industry. It's not easy to obtain. It's expensive, but you can find YouTube videos of people like drinking a little and playing around with it. So it's called heavy water. The other isotope of hydrogen is called tritium. That has 2 neutrons and 1 proton. So that has up to 3. That's why you have the 3 here. And this is an example of a radioactive isotope. If you get some tritium together, it will decay away and release X-rays and gamma rays. Okay. It has a half-life, we say, of 12 years, so it takes about 12 years for it to reduce by half as it decays away. They used to make watch dials by putting tritium in them. That would make them glow green due to the radioactivity. Okay, they don't do that anymore because it's a little bit of a cancer hazard. So you can make a periodic table which shows just the atomic numbers, so the number of protons, but a slightly fancier version of the atomic periodic table is called a chart of nuclides, which allows you to include not only the atomic number on the y-axis, but also the number of neutrons. So if we go along the x-axis, those are different isotopes. So if I look at, say, carbon, so carbon-6, we see that carbon-6 has like 10 isotopes, and the stable ones are shown in red. So there's a couple main isotopes of carbon, carbon-12 and carbon-13, that are stable, but all the other ones decay radioactive, are radioactive and decay away. And here down in the way lower left, you see those examples of hydrogen. You see hydrogen, deuterium, and tritium. So for example, so this is showing off like the amount I kind of want you to know about this for your quizzes. You have a gold atom, okay? The nucleus of a gold atom contains 79 protons and 118 neutrons. What is its atomic number and its atomic mass number? The atomic number is the number of protons. So the atomic number is 79. The mass number is when you add the protons to the neutrons together. That gives 197. So the only, the mass of an atom is almost completely determined by the number of protons and neutrons. The reason why we don't say anything about the electrons is because an electron is 1,000 times less massive than a proton or a neutron. So we can ignore the masses of the electrons. Okay, any questions about this kind of basic but whirlwind, I know, overview of the constituents of matter, right? Atoms and what make up atoms, which are protons, neutrons, and electrons. Okay, so we have light, we have matter, they interact. That's how we see light, and that's how we can produce light, and right, it bounces off matter. That's how we can see things. So at the microscopic level, these are the 4 ways that light can interact with matter. Okay, there's something called absorption and ionization. So, for example, an atom absorbs light and it shoots off an electron. Okay? I give that as an example of what can, what ultraviolet light can do to your skin. That's called ionization, and that can damage your skin. You can have absorption without ionization. Okay, and what that does, that's when, like, say, visible light hits your skin. Your skin absorbs the light, and then some of that light is turned into heat, or some of it gets re-emitted back out. Okay, you can have scattering, for example, Compton scattering. That is, light scatters off matter. That will correspond to reflection. Okay, and then there's this very kind of esoteric kind that you see in particle accelerators, So it's not as relevant here, but you can have actually light created when you annihilate particles and antiparticles. That's another way that light can interact with matter. Okay, so if we go to the large scale, what do we see? We see things like emission of light. Okay, that's when you, for example, in a light bulb, you heat up the wire in a light bulb. It gets so hot, the electrons start moving around, and light gets, things are jiggling around, and light starts getting emitted. You can have absorption, so it's kind of the opposite. Flashlight hits a piece of, hits your wall, and some of that light just causes the atoms to jiggle around and warm up. Okay, but the light is absorbed. You can have light just transmit, like through a window, and it can also get reflected or off the window, or it can scatter off clouds. Okay, so those are the ways that light can interact with matter, and some of these will be very relevant when we talk about light coming from stars or from nebula. Here's just one picture. It's not. What is meant is just to kind of show off that all this stuff is going on in any picture or any time you take in your surroundings, and you kind of take it for granted. So, for example, you look at the trees; they're green. Well, why are trees green? Well, they're being hit by white light from the sun. Well, white light is a combination of all the colors of light. Okay, so why do they look green? Well, some of that light is absorbed, and some of it is reflected. So the stuff that's reflected is green, and everything else is absorbed. So it's absorbing red and blue and yellow, but it's not absorbing green. Okay. There's the sky. Why is the sky blue? Okay, this is a famous question. Why is the sky blue? One myth is that it's blue because of the oceans. That's not true. It's just as blue above the middle of the desert as it is in the oceans. The sky is blue because of scattering. Air, it turns out, scatters blue light more than red light. And so if that weren't true, when you looked up here, you would see the stars. It would be black, right? Because the sun is really bright. Or else it would be outer space. But the reason the sky is blue is because that light from the sun gets scattered in random directions. So that by the air. So when you look up, try to look at the stars, what you're seeing is that scattered blue light. What else are you seeing? Well, we're seeing clouds. Clouds are white. Why are clouds white? Well, you have the sunlight is white, and the clouds are randomly scattering all colors of light equally. So it's taking that white light and scattering it all randomly. That's why that is white. Okay, so those are some examples. So here's a question based on what I was just discussing. So let's give you another opportunity to get some participation points. Why is the sky blue in daytime, of course? I'll give you 5 more seconds here. Okay, I'm ending it. And most people got it right, as we were just talking about. Air molecules scatter blue light more than red light. So look up at some random patch of the sky. Light from the sun is say going across your field of view like this, but you can't see it, but it scatters luckily toward your eye. And I'll show a picture of that in a second. Just to try to drive this point home. So you're looking up at the sun. Now, if you look directly towards the sun, if light scatters blue light, that means it should look a little red. right, the light from the sun going towards your eyes actually starts to get a little red because the air keeps scattering blue light. And that's true, right? That's why the sun looks a little bit yellow when in fact it's kind of white color. And at sunset, the light has to go through more air. And that's why the sun looks redder at sunset. Meanwhile, if you're this person over here and you're looking this direction towards what should be the stars in the night sky, you see all that blue light that's been scattered away. And that's why the sky looks blue. Any questions about this? So here's another example. So, here's just any type of material that you see that has a color, right? What's going on, right? So, well, the reason why you can see anything at all is because it's being illuminated from the outside by light, in this case, say by the sun. So white light. So you have all these colors of light hitting it, but it's reflecting, in this case, red light. That is, it's not absorbing red light. Now, if the star, let's go through each of these, right? If the star absorbed red light, then it wouldn't be red, right? Because it would be taking away the red. It might be blue or green, for example, if it absorbed red light. If it transmitted red light, then it would be transparent, right? You would see, the light would just go back, the red light would go and hit the rock behind it. If the star emitted red light, then you would see it at night, right? But it doesn't glow at night, red, right? We see the star during the day because it's reflecting the red light out of all of the colors of light that are hitting it from white light. Okay, so as a recap, light is a form of energy, okay, right? We talked about all these forms of energy, kinetic energy, potential energy, thermal energy, potential energy also not just in terms of taking something higher, like climbing up a ladder, but also in the form of chemical bonds, right, and calorie, fat or gasoline. But in addition, right, a form of energy that's how we get warmed up by the sun, right? This energy from light is traveling through space from the sun, reaches the earth, and luckily it hits the molecules in our body, causes them to jiggle around and get warm. It's a form of energy. And it's composed of these individual particles called photons that each have an amount of energy determined by their frequency, or equivalently their wavelength. There's all these different kinds of light that are characterized by their frequency or wavelength, from radio waves to red and blue up through gamma rays. And ordinary matter is made of atoms. They're made of electrons, protons, and neutrons. And these things interact with light. Right? Light, which is made of electromagnetic fields. Electric fields interact with charged particles, okay, like electrons. So light can scatter off atoms. They can be absorbed by atoms, and atoms can emit light or just scatter off. So the next topic, and the most, where we're going towards, because it's really relevant to astronomy, is how do you get information from light, right? How does light tell you about what things are made out of, where things are, what their speeds are? So that's the next topic. We're going to learn about spectra. Okay, this is going to be ways that you can tell what something's made out of from light. Also, not only what things are made out of, so this is just remarkable how much we can learn from light. We can learn from what things are made of, but also what their temperature is. We'll also see we can learn about how big something is, because the larger it is, the light. But also it tells us the speed of distant objects. So we can learn a tremendous amount by looking at the light from things that are very far away. So spectra. Okay. Spectra is a word that stands for all of the different frequencies or wavelengths of light that are reaching your eyes or a sensor. And Kirchhoff in the 1800s invented or realized that there are basically three different kinds of these spectra. You can have a spectra that looks like this first bullet point, where you're emitting a continuous range of frequencies. In other words, colors or wavelengths of light. So you might see a spectrum that looks like this. You have violet, you have blue, green, yellow, orange, red, all mixed together. And an example is like a light bulb. Okay, and a light bulb produces, whitish light or a glow of it's kind of orangey, but it's blue. If you put it through a prism, you see there's blue, there's green, there's red, all mixed together. Okay, but there's two other types of spectra that you might not be as familiar with. There's what's called an emission line spectrum, which is that if you take a little bit of gas, and you put it in a tube, and you heat it up, and then you put it through a prism, you might see something like this. Okay, instead of seeing a rainbow when you put it through a prism like this, you see a very specific red, a very specific blue, a very specific violet. This is called an emission line spectrum, and as we'll talk about, that's characteristic to a specific type of atom. And then there's the inverse of that. That is, if you take a cold gas, and instead of heating it up, you just let it absorb light, the opposite will happen. You will see little absorption lines. That is, a continuous spectrum will show that there's certain very specific wavelengths that are absorbed by that gas. So you see the opposite. You see little shadows or little lines that are called absorption lines. And in this way, we can learn what things are made of and their temperature. So here's an example of a continuous spectrum, like from a light bulb. That is, we could have plotted wavelength or frequency on the x-axis. But let's say wavelength. That is, you're going to have some short wavelengths like blues and violets. You're also going to have some long wavelengths like red and infrared and microwave. But you could have a line spectra like this, where you have a very specific wavelength, say violet, a very specific amount of red and a very specific amount of infrared or something. And so how do you get these line spectra? Well, there's two kinds. There's the emission line spectrum. That is, you take a gas and you heat it up. So if you take a gas and heat it up and you look at it, what you'll see is, instead of like a light bulb, you see, and I'm assuming here you have a gas of just one type of atom. You'll see that specific atom's characteristic type of light that atom likes to emit. And it might be a red and a blue and a green. That's what you'll see. That's called an emission line spectrum. If you take that same gas, but don't heat it up and just let white light fall on that gas, then when you look at that white light, it will absorb certain lines. It'll absorb those same lines. So absorb, say, red, absorb, say, blue, and absorb, say, specific green. And where does this come from? Well, let's look at, say, hydrogen. So hydrogen is an example of one type of atom. And remember, light comes in little packets called photons. And how do you produce photons from hydrogen or any other atom? Well, you need to cause the electrons that are orbiting the nucleus, so in this case, the electron orbiting the single proton in hydrogen, it has to fall from a higher energy to a lower energy. And then that energy difference is the energy that the photon gets as it flies away. Okay? And so if you heat up an atom, you can warm it enough that the electron jiggles up to a higher energy level and then falls back down and emits a wavelength of light specific to that specific energy level difference characteristic of that atom. So these are the famous specific energy levels for hydrogen corresponding. So you can have an electron falling from the first highest, well, here's the lowest energy orbit, the next highest energy orbit, and if the electron falls from here to here, it emits a specific wavelength of light. It's an ultraviolet ray of light. Or you can have an electron falling from the third to the second energy level, producing red, or from the fifth to the third, or fourth to the second, producing blue, and so on. And in this way, you get a very specific set of specific wavelengths of light from hydrogen. And it's going to be different from helium. It's going to be different for carbon and oxygen. They're all characteristic of that particular element. And you can go the other direction. If I take cold hydrogen and hit it with light, the opposite happens. Light comes in and it takes the electron, and the electron gets bumped up to a higher orbit, and the light is absorbed. And it's those same wavelengths of light that get absorbed. Whether the light hits an electron going from here to here, an electron going from here to here, or from here to here, those correspond to specific wavelengths of light that are absorbed or emitted. So we would do this in class. If we were in class, I'd heat up some light in one of these gas tubes and give you little prisms to look at the light through. But pictures will have to suffice today. So if I take, for example, hydrogen and heat it up in one of these tubes, it'll look red to your eye. But if you put a little prism and look at it, you'll able to see that actually this light from this tube doesn't look like a nice rainbow like it would from a normal light bulb. You get very specific wavelength of red, a very specific wavelength of kind of light blue, and then a dark blue, and then a violet. Here's helium. So helium has a different spectrum. So if you look at helium, it looks more whitish just with your eyes, but you put it through a prism and you get red, yellowish orange, light blue, darker blue, very specific wavelengths of light that are coming out. And in this way, if I look, say, at a star this way, I can see, is that star hydrogen? Is it made of helium? Because I can put it through a prism and I see exactly what wavelengths of light come out. So this is how we can tell what things are made of in outer space, just by looking at the light, because you get these very characteristic, it's like the DNA code of different elements out in space. You can see very clearly what they are from their spectrum. Here, for example, is the solar spectrum. So the sun, okay, is mostly producing a continuous white light. We're going to explain in a bit why that is. Okay? But it's mostly producing a continuous spectrum. Okay, so how do we, in this case, for the sun or for a star, what are we looking at when we talk about what we can see from its spectra, what it's made of? Well, it's because that white light from the sun is shining through the outer atmosphere of a star like our sun. So the sun is producing white light, meaning all wavelengths of light continuously from red through violet, but that light is shining through the gas in the outer atmosphere of the sun and producing an absorption spectrum. And that's what all these dark lines are. Okay, all these dark lines correspond to all the elements in the outer atmosphere of the sun that are absorbing light from the sun. And so we look at those and it tells us exactly what is in the atmosphere of the sun. By the way, this would be all one long single line, but it has to be wrapped around in order to show you on one page, right? So this is on the far left, maybe it would be infrared and then red, and then it would keep going all the way to the right where it goes through yellow and green and blue and then violet. I'll talk about this later, G-type. The sun is a G-type star. Okay, so any questions so far about spectra? Someone's chatting, but maybe some people don't have microphones that are working, but it's always easier to just hear you say something out loud.
Yeah, no questions, Professor.
Some point, so yeah, go ahead.
What kind of device do you measure this with?
Yeah, so in the simplest case, it really is just a prism. So the simplest way of making a spectrum, which you're all probably familiar with, like in your windowsill, you have maybe a piece of glass, right? White light comes through it, and it spreads that light out into a rainbow. And that rainbow shows you all of the colors that are in that light. And of course, physicists use a more sophisticated version of the same thing, but it literally is the same principle. So we can take light, from a telescope, and we put that light through a prism, a very fancy prism, and it shoots out all the light. It spreads it out like a fan, and then we can sense very accurately all along that light, how much red, how much blue, how much green, how much violet, and so on.
Okay, cool, thank you.
So I mentioned infrared is most associated with just what our bodies are emitting. That's a result of the fact that all objects are constantly emitting light. Okay? It's called thermal radiation. It's the consequence of being warm. That's why it's called thermal radiation. It's not just us, so we are emitting mostly infrared, but stars, right? Starlight, it turns out, is an example of the same kind of thing, but stars are hotter. And because they're hotter, they're not just emitting infrared, they're emitting visible light. And we're all actually kind of familiar with this, even if without maybe realizing it. Like if you take a fire poker and you put it in the fire, well, first you'll be able to feel the warmth, that's infrared. And then you get it hotter and it'll start to glow dark red. And you get it hotter still, it starts to glow brighter red. You get hotter still, it starts to glow orange. Eventually it glows yellow. If you get it hotter still, it starts to glow white. But what is white? Well, white, remember, is all the colors of the rainbow. So what happens is it starts to also glow blue. So now that looks to your eyes like white once you have blue plus red and green, right? But as you get hotter and hotter, it starts to glow in higher and higher frequencies or shorter and shorter wavelengths. Eventually, it starts to emit ultraviolet. That's why welders need to wear big welder goggles, because what they're doing is producing something so hot, it's emitting a lot of ultraviolet radiation. And if you did it hotter still, it would start to emit X-rays. So the spectrum, and it's called the black body spectrum, depends on something's temperature. We mostly emit infrared, including anything that's at room temperature is mostly emitting infrared. But you get it hotter, eventually it starts to glow red, and then it starts to glow into the greens and blues and so on, okay? Here's an elephant looked at through a thermal camera, meaning that's its infrared glow. Okay, we're all glowing right now in the infrared. So the technical term for this is called black body radiation. That means any object that's I don't want to get into the details, but it's called black bodies because it has to be the type of material that kind of absorbs and emits light. So not the air. Air is not a good example of a black body, but most things are things that absorb and emit light. And anything that has a temperature, then that's one of these objects emits light. And this is the law. The law is called the Stefan-Boltzmann law, and it says the luminosity, L. Now, luminosity is the total amount of light energy in watts that's emitted. Okay. So, for example, your toaster oven has a luminosity of like 2,000 watts. Okay. The Stefan-Boltzmann law tells you that that total luminosity is equal to a constant, sigma, times the area of your object, times the temperature to the fourth power. Meaning, you want to know how much light energy is going to come off, say, your body? Well, you need to know the area of your body. Bigger bodies emit more, and the temperature. The higher your temperature, the more light you're emitting. Okay? This is, by the way, is why if you have a higher body temperature, you are emitting. You're losing more calories. You're emitting more energy. And the same is true of stars. Okay, a star is a larger star, has larger area, so it's emitting more luminosity, more light energy. But also, if the star has a higher temperature, okay, higher temperature stars emit more light. Okay? That's called the Stefan-Boltzmann law. And then the second law that relates to what I just mentioned about the hotter something is, it starts to first emit infrared, then red, then yellow, then green, and blue. This is called the Wien's displacement law. Okay. All it says is the higher temperature something is, the higher the frequency, or the smaller the wavelength of the light. So in terms of wavelength, this law can be written as the peak of the wavelength, the peak wavelength, times the temperature as a constant. Meaning higher temperatures mean shorter wavelengths. So for example, an object is kind of hot, so it'll be glowing red. But you get it hotter, maybe it's glowing yellow, so it has a shorter peak wavelength. Really hot, it's starting to glow blue, so it has an even shorter wavelength. By the way, the peaks are getting higher here due to the Stefan-Boltzmann law, because as they get hotter, they're also emitting more light while they're getting bluer. So these are the two main ingredients that really help us understand by looking at light, say from a star, about the star's temperature and its size. So, for example, so I'll leave you today with this example. The sun, when we look at the sun is about 5,800 degrees Kelvin. Okay, the surface of the sun, that's all we can see. We can, we see the surface of the sun. It's about 5,800 degrees Kelvin. And we can apply the Wien's displacement law. Okay? Wien's displacement law says the peak, the wavelength where the most energy from the sun is coming has to, when multiplied by the temperature, has to be this constant. So if we plug in, meaning divide both sides of this equation by that 5,800 degrees Kelvin, what do we get? This is the wavelength of light we get. The peak wavelength of light from the sun is about 500 billionths of a meter, 500 nanometers. That's in the visible part of the spectrum. In particular, it's green, okay? Green light. So this might seem weird because the sun doesn't look green. The sun looks white because it's emitting, as we discussed, a full continuous spectrum that contains red, contains yellow, green, and blue, and altogether that looks like white. But the peak, the most amount of light is green coming from the sun. And an interesting fact about the human body is the human eye is most sensitive to green. Okay? I don't think this is a coincidence. It makes sense that biologically we would have evolved to be most sensitive to the kind of light that is most common coming from the sun. Okay. All right, so that's, I think, a good place to end today. Is there any questions about anything at all?
No questions for me.
All right, have a good weekend. I will see you Monday.
Have a good weekend, Professor.
Thank you, Professor.
Thank you, Professor.